Good afternoon, everyone. Thanks for coming to this week's webinar offered by Synchrotron Earth Environmental Science. It's my pleasure today to introduce our presenter, Tom Toellner. Tom is a physicist in the X-ray Science Division at Argonne National Lab, and he will be talking to us about nuclear resonant spectroscopy at the Advanced Photon Source. If you have questions that you'd like to ask Tom over the course of the talk, please enter them in the chat or hold them, and you can raise your hand using the Zoom raise hand function at the end of the seminar. In the meantime, please remember to keep yourself muted until you're asking a question after the presentation. Tom, it's all yours.
Thank you, Randy. This is an update of the experimental capabilities for performing nuclear resonant spectroscopy at the APS. I'll start by giving a sort of brief review of the scattering techniques and the information that can be extracted from the measured data. I'll focus mostly on geoscience, and that seems to be the audience, of course. I also present a new approach for performing Mössbauer spectroscopy in the energy domain that can be used during any synchrotron operating mode at the APS. And that's probably the most significant change to the program post APS upgrade. So low energy nuclear resonances, typically when one thinks of nuclear resonances, they're generally in the hundreds of keV to mega electron volt range. But there are some isotopes that have very low energy resonances. These exhibit a Mössbauer effect, which is a recoilless resonant absorption. And this happens when the typical atomic vibrations are of the order of the wavelength of the transition radiation. Or smaller, then you get a strong Mössbauer effect, and that allows these techniques to take place. And at lower energies, we also can access them with synchrotron radiation because that's where hard X-ray synchrotrons have the most spectral power. And they give some isotope selectivity, so that allows us to probe rather specific areas of a material. So I'll cover two techniques. The first technique is the vibrational spectroscopy that goes by multiple names or acronyms. One is inelastic nuclear resonant X-ray scattering or nuclear resonant inelastic X-ray scattering. There's different acronyms. I just happen to call it vibrational spectroscopy. This probes the interatomic potential at the nuclear resonance site. So just at, for example, iron, and I will focus mostly on iron during this talk, but the same applies to the other resonances as well. Probing interatomic potential allows you to access vibrational and elastic properties of the material. It also allows one to extract the partial phonon density of states for the resonant atom, and this gives a wide range of thermodynamic information that is related to or derived from the density of states. And some of these are the sound velocity as well as isotope fractionation, which are popular in the geoscience community. The other technique was Synchrotron Mössbauer Spectroscopy. This exploits the nuclear moments of the iron isotope, such as the magnetic moment, to probe the magnetic ordering or spin state of the material. A quadrupole moment allows you to be sensitive to electric field gradients that are related to the bonding environment of the iron atom. And also the nuclear volume probes the s electron density, and so is sensitive to any changes in valence or oxidation state. So there are a number of nuclear resonances, say below 40 keV, where source strength is strong, but there's still a number of sort of determinative factors that can limit their suitability. One, of course, is the strength of the Mössbauer effect. As one goes up in energy, the magnitude of the effect drops, typically for very high energies. 60, 70, 80 keV samples would typically have to be cooled cryogenically in order to measure a reasonable signal. This places some limitations on experimental environments and stuff like that. So that's something that always comes into play. The nuclear properties such as cross-section or internal conversion coefficients, these can affect their suitability. The lifetime of the resonance, I'll show that this is the predominant aspect of the resonance that allows us to separate nuclear resonant scattering events from the vast majority of electronic scattering that goes on from a sample. And of course, available technology, optics and detectors, it's easier and generally more developed to produce narrow bandwidth optics for lower energy resonances than it is to do that up at 70, 80 kilovolts. And then in the end, of course, user demand dictates which resonances we focus on. So at the APS, we have capabilities to do iron, of course. That's the most dominant isotope that people exploit. We also do europium and dysprosium. These are done at beamline 3ID. And then tin 119 is available at beamline 30ID. We also have optics and capability to do krypton, but user demand is quite low, so it's generally not offered. So as I mentioned, there's a time filtering technique that allows us to separate these. This stems from the fact that the nuclear level line widths are extremely narrow in sort of the 10 to minus 10 to 10 to minus 7 electron volt range. And this gives them a long decay time, typically nanoseconds to, excuse me, to hundreds of nanoseconds. In the case of iron 57, the nuclear level lifetime is 141 nanoseconds. And this is the primary aspect that we use to exploit to separate these events. So the synchrotron radiation is pulsed, and the pulse width is typically a couple hundred picoseconds at the APS post-upgrade. This is very narrow compared to the lifetime. And so this allows the possibility to do time discrimination. Another aspect is the pulse is extremely strong. Typically in the case of beamline 3ID, in a 2 eV bandpass after a high heat load monochromator, for example, we have 10 to the 7 photons in one pulse. And that pulse, like I mentioned, is a couple hundred picoseconds long. So that's a very strong excitation pulse. That's too much for fast nanosecond resolved timing detectors to handle. So that needs to be reduced in some efficient way without limiting our nuclear resonance scattering events. So in a flash, the plot in the lower right-hand corner shows a log of the intensity. So you see a spike that corresponds to the prompt non-resonant scattering, and then the delayed. So that prompt will typically have 10 to the 7 photons in it, and then the delayed will typically have nothing, actually. Occasionally, we'll see one event after a flash, and extremely rare you would see 2 events. You would have to go to a free electron laser in order to get any probability for 2 or 3 photon events in that time window. That's after one flash. So generally, the measurements are such that, of course, we repeat the measurement over and over again and accumulate those resonant events over time. The normal way we deal with the 10 to the 7 photons per pulse problem is to reduce the bandwidth as much as possible that we can do efficiently, and then use time-gated detectors to gate whatever is left over. There are a number of other techniques that have been developed over the past couple of decades. I will not go into any of those, but they're also there. But the reducing the bandwidth, the high resolution monochromator is by far the most common approach. So changes that come with the APS upgrade that are relevant for us are, of course, it's a low emittance electron beam. This reduces the horizontal X-ray source size. The vertical X-ray source size hasn't changed that much, but the horizontal has changed significantly. This allows us to efficiently focus to 1 micron. This is important. In nuclear resonance spectroscopy, signal rates are generally low because of the bandwidth is so low for the resonance. And so doing things efficiently is extremely important. We try not to throw away flux any more than we absolutely have to. So we can now focus down to 1 micron efficiently as a result of the low emittance storage ring. Prior to the upgrade, we had 3 timing modes. This corresponds to the location of electron bunches in the storage ring. And this determines the pulse structure in time of the X-rays. So we had a 24 bunch mode, which had 153 nanosecond dark time, and a hybrid timing mode with a 1.6 microsecond dark time. And these were typically used for nuclear resonance scattering. And 11 nanosecond was a 324 bunch mode, which we could not use for nuclear resonance spectroscopy. The 24 bunch mode and hybrid timing modes have been discontinued and replaced with a 48 bunch mode post-upgrade. The 48 bunch mode has, as a result, half the dark time. So the pulses are 76 nanoseconds apart. And this is notably smaller than the nuclear level lifetime for iron, which was 141 nanoseconds. And consequently, it's going to adjust our way we do Mössbauer spectroscopy. And I will get into more on that later. The flux, currently in 48 bunch mode, we're getting about 90% of what we had pre-upgrade, but that's because the current is restricted to 130 milliamps. But that is projected to improve over the next couple of years to 200 milliamps. And then we expect to get 140% of the pre-upgrade flux as we have in 324 bunch mode. So this is the standard setup for vibrational spectroscopy. We have a pre-monochromator that just deals with the enormous heat load coming from the undulator and reduces the bandwidth down to 2 electron volts at 14 keV. And then we have a tunable millieV monochromator. Typically, it's 1 millieV for all the resonances, and that produces a beam of 1 millieV bandwidth at the nuclear transition energy. And in this case, the mono needs to be tunable. So typically we tune plus minus 100 millieV far enough so that we can still see phonon excitation either by annihilation or creation in a spectrum. So you see you have an elastic line when the incident beam is aligned to that, and then you see the 2 side bands. And so the mono needs to scan. All you do here is you scan the monochromator, you scan the incident energy, and basically time filter out any resonant events that occur between the X-ray flashes. Here, the width of time window is not critical as long as it's reasonably not too small, so that we have some reasonable time window. So 76 nanoseconds between pulses is actually a benefit in the case for iron 57. There's something like a 20% gain in the signal rate because the time average excitation or decay rate is higher, simply because the pulses are not too far apart. So there's a little bit of benefit there actually in the case of vibrational spectroscopy. These are just some of the monochrometers that are used. The one in the upper left-hand corner is what is used for the iron resonance. All of these involve silicon crystals that are configured in a way to introduce a lot of dispersion and then remove that dispersion, preferably, in order to achieve a 1 milliV bandpass. 1 milliV is about an order of magnitude better than what you can do with just single crystals by themselves at this energy. And so it's a way of getting past that crystal back reflection limit in energy bandwidth. The detectors are silicon-based avalanche photodiode detectors. These are detectors that are capable of detecting individual photons with a very fast time response of about 1 nanosecond and extremely low noise, which is also very important, and a large dynamic range, so they can handle a pulse and then respond rather quickly as well. For the focus beam, as part of the upgrade, we got a new Kirkpatrick Baez mirror system. This achieves about a 1 micron spot size, but this is without a high-resolution monochrometer. When we introduce the iron high-resolution monochrometer, this degrades the focusing performance down to about 12 microns by 2 microns, but it's still, most users will be okay with this level of focusing. But we're exploring means to sort of replace this monochrometer to mitigate the focusing degradation. This is just due to uncompensated dispersion inside the monochrometer. So the information, so the spectrum, you have the elastic line and the sidebands. These are data shown on a log scale, you see. So that the plot on the left shows the raw spectrum. This has to be normalized in order to obtain a phonon excitation probability density. And there's a rather robust procedure for doing that by just making the first moment equal to the recoil energy of an iron 57 atom that's absorbing a 14.4 keV photon. That recoil energy is 2 milliV, and so as long as the first moment of the spectrum is equal to that, you then have the phonon excitation probability density. From that, you can apply a procedure, a Fourier log deconvolution method, that allows you to extract the partial projected phonon density of states. This is done with software that we have available. This is Phoenix software, and I will show you where you can get that software and more later. So one of the quantities of interest for some geoscientists is the Dubai sound velocity. This is determined from the low energy region by looking at the curvature of that Dubai spectrum, of the density of states in that region. Once you have the Dubai sound velocity, you can get the compression and shear velocities from the equations on the left. You have two equations and two unknowns, and if you solve, you need to provide the adiabatic bulk modulus and the density. Density is typically gotten from diffraction data, which can be taken at the beamline, and so then one can get both shear and compression velocities, and then you get the Poisson ratio as a benefit as well. Another quantity of interest is equilibrium isotope fractionation factors. It's popular amongst geochemists. One approach is to determine it from the kinetic energy. One can get the kinetic energy per atom from the second moment of the phonon excitation probability density. Unfortunately, it's a little bit sensitive to the background because being the second moment, that's an even moment. The background is also an even moment, so has a non-negative second moment. And so this background subtraction becomes an issue. As a result, Nicholas Dolphus came up with an alternative approach using the third moment as an odd moment, so it gets around the background subtraction issue, or at least reduces it, let's say, and you can get the fractionation factors using that moment. You can also get it from the second moment of the DOS. Either way can work. For doing these measurements, it's very important to get the entire spectrum, including multiphononic parts of the spectrum. So the scan range is quite critical, and background determination is also important generally. Some other quantities, the column on the left are quantities you can get directly from the S of E. One is the temperature, just from the detailed balance, of course. Another is the mean square displacement. This is just gotten from the area under the curve minus the elastic line. And then, of course, as I mentioned, the kinetic energy can be gotten from the second moment of the S of E, and the average force constant. Actually, it's the second derivative of the interatomic potential along the beam direction, but you can assume it's a constant at a fixed temperature. If you assume a quasi-harmonic lattice model, you can extract the density of states and all the quantities that come from that, of which there's quite a few. And then there's the Dubai sound velocity, as I mentioned. You can also get the Gruneisen parameter if you take multiple data sets and vary the volume or the density, of course, and then you can extract a Gruneisen parameter. For the second technique, the Mössbauer spectroscopy, here we're going to look at the measuring the hyperfine interactions. These are interactions between the nuclear moments and the fields generated by the electrons. One is the isomer shift. This is results from an overlap of electron density at the nuclear volume, and so it's very sensitive to s electrons. And as a result, it probes oxidation state and valence, which are very sensitive to s electrons. Quadrupole splitting, you measure the presence of an electric field gradient, which is very sensitive to the electronic bonding and just the general electronic configuration. And because the nucleus has a magnetic moment, you can probe the coupling to the local field. So you can tap into sort of like the magnetic ordering or the spin state of the sample. Now, unlike the vibrational spectroscopy that you can extract straight away from the data without fitting, you can also fit it using DFT, but and some users do that, of course, depending on what kind of information one wants to attain. But in the case of Mössbauer spectroscopy, one has to construct a model of the hyperfine interactions on the sample. And so each nuclear site needs to have a set of nuclear parameters defined, and then one can generate a spectrum, which, and we have fitting software that does this. This is CONUS software, and that is used by the users to fit the data. The spectra themselves can be done in two different ways. One is in a time domain. This is usually done in a forward scattering geometry, but one can also do it by Bragg diffracting from a crystal that contains the resonant isotope. Generally, nuclear forward scattering is preferred because you do not need high quality single crystals for this. You can do any variety of samples as long as they're solids. And this approach for Mössbauer spectroscopy is applicable when the interpulse spacing between the X-rays is longer than the nuclear level lifetime. And this remains the case after the upgrade for tin 119 and europium dysprosium. They're all like in the 10 to 30 nanosecond nuclear level lifetimes. And so the approaches there will remain the same. In the case of the iron 57 with a longer lifetime, we have to introduce an energy domain approach in order to get a sufficiently wide time window for sort of meaningful extraction of a spectrum. There are some things you can still do with the narrower spectrum, but the vast majority of samples that one wants to measure with the Mössbauer spectroscopy need a larger time window. And so we will convert to an energy domain approach and provide that to the users. So the time domain approach, the setup looks very similar to the vibrational spectroscopy. The only difference is the milliev monochromator is left stationary. We do not scan the incident energy. We simply go to the nuclear transition energy and the mono sits there. And then we do time differential detection of the X-rays that come off the sample. The detector has to be placed further from the sample to avoid any incoherent scattering. Incoherent nuclear resonance scattering, that is, so that you just get the forward scattering signal. This requires 48 bunch mode, and this will be the approach that we use for tin, europium, and dysprosium. This is sort of like the native approach to do nuclear resonance scattering or Mössbauer spectroscopy at a synchrotron, given it's a broadband pulse, a pulsed source. You excite all the resonance in the sample, and they interfere with each other. So it's an interferometric approach, which leads to a rather complex time decay, but doesn't involve introduction of any other resonant absorber in order to determine the hyperfine structure. For the case of iron 57, we will do an energy domain approach. This is a new approach. The other synchrotrons also offer. Our approach is a little bit different than theirs, but in the end, it's still going to generate a Mössbauer absorption spectrum. This requires we introduce a secondary source, gamma ray filter, if you will, that generates gamma rays that have some nano EV of line widths. At the same time, it has to get rid of all the non-resonant radiation, which would contaminate an absorption spectrum. The net result is we end up with a setup that's rather similar to a traditional Mössbauer spectroscopy setup, where one scans the energy by moving the gamma ray source on a velocity drive and then correlating that with the arrival time of the photon in order to bin all the events as a function of velocity, and velocity corresponds directly to energy. And this can be done in any timing mode, and the result is going to be a convolution of the gamma ray source with the sample. That is what the measurement involves. So to generate this gamma ray source, we're going to use some polarization filters. So if you start from the left, the synchrotron radiation is already highly polarized, but it still needs to be cleaned up because we cannot have any contamination at all. At least we would need to reduce that to well below the nuclear resonance signal. So what we do is we introduce a horizontal linear polarization filter. This purifies the polarization to probably a part in 10 to the 11 or so. Actually, no, part 10 to 9, sorry. The beam excites the nuclear resonances in a magnetized alpha iron film, and this film is mounted on a Mössbauer velocity drive. After the film, there's a 6-line spectrum, combination of left circular, right circular, and linearly polarized radiation. And then it goes to a vertical linear polarization filter that gets rid of any sigma polarization that comes from delta M equals 0 transitions. And then we're left with just a pure polarized beam that has the 4-line spectrum that you see there. You see the lines 2 and 5 of the standard 6-line Mössbauer spectrum are missing, but this 4-line spectrum will be the source spectrum that we will use. This approach has some real advantages in terms of stability because it's a forward scattering approach. It doesn't impact the focusing capability, so that's why we're going with this approach. And also the emitter is alpha iron, and so which is a standard isomer shift reference material. Isomer shift is it's just a benefit. The focusing is done. This takes advantage of low emit storage ring, of course. New KB mirror allows us to get down to 1 to 2 microns, and the polarization optics will be designed so that they preserve the X-ray beam emittance, and so there's no source broadening that might occur otherwise. It's the kind of broadening that we're avoiding that happens in the iron mono and the vibrational spectroscopy. So that will not be there. So we'll be able to focus down to 1 micron. The sample environment, there's a bit of a change going from time domain to energy domain. In time domain, one has sort of an excess or surplus of resonant photons that we have to throw away because the prompt flash on our detector is too much. So we end up putting an absorber in front of our detector to protect them. And then if a user environment or sample absorbs a lot of excess radiation, we just remove the absorber in front of the detector to compensate. That approach doesn't work in the energy domain. Here we have to minimize the amount of absorption in the sample and as well as in the sample environment. So diamond anvil cells, for example, the diamonds should be milled out from the backside to limit the absorption losses in the diamonds. Another issue is vibration. In time domain, you don't have to worry about vibrations at all. In the case of an energy domain, vibrations can ruin the spectrum, and so one has to consider using low vibration cryostats and also mounting samples securely on a mount so that they cannot vibrate. For the detector, we'll just use a sodium iodide. We don't need we need photon counting capability, but we do not need any timing capability. And so we just use the detector with the maximum efficiency, which in our case will just be the sodium iodide on a photomultiplier tube. It's also possible to detect a conversion electron Mössbauer spectroscopy, so we can detect electrons. This is not really currently in the scope. Detecting electrons is not really a problem, but imaging a 1 micron beam on the sample is something we have to consider. Since this is on the opposite, this is not on the downstream side. SEMS comes off the front surface of a sample. One needs imaging there. So it's just a question of whether or not users are interested. So if you are interested, please email me and let me know what kind of samples you have and if you're interested in SEMS. To test this setup, I put together a little test setup prior to the APS going down for the upgrade. This was not an optimal, so counting rates were quite low, but it basically employed everything I needed to find out where some issues might be. In this case, I just used a 12 micron unenriched iron foil, and I put that on a Mössbauer drive and put them between 2 linear polarization filters. The sample was an iron 57 foil, 2 microns thick. This is 95% enriched, and we collected. This spectrum took 7 hours to collect. That's a long time because the counting rates were low. What it does show, though, is the stability is quite excellent because the fitting was straight away. There was no additional broadening one had to introduce. This was something I was concerned about because the emitter and the sample are on different tables, actually, and so tens of micrometer per second vibration velocities can affect the data. This setup just had a 20 micron spot size, but this will be improved to 1 micron. And Kona software has been modified by Wolfgang Sturhan to allow an arbitrary energy source spectrum so that one can fit. And the 4-line spectrum is available to that package as well. I measured a variety of spectra in addition to this iron foil, so I'll show that just to give you a sense. And but first I had to characterize the source. For that, I used a different spectrometer altogether. I used a fast shutter spectrometer that was being used during hybrid mode at Beamline 3ID. And that allowed me to get a very long time window, so I could take a time spectrum over a long time period. So this is the time spectrum of that iron emitter, and you can see the fit is quite excellent. This is kind of normal if you know the hyperfine parameters really well. A nuclear resonance spectroscopy can be quite accurate in terms of fitting the data. You see it kind of breaks down after about 400 nanoseconds, and that's because the iron foil was not completely magnetized. So the magnetization field should be stronger. But the impact on the energy spectrum is pretty minimal. But for the new instrument, I will have a stronger magnetic field so I can saturate the magnetization and just to make it more clear exactly what the spectrum is. And then when one introduces polarization optics, one arrives at the 4-line spectrum shown on the right. You get all the hyperfine parameters you need from the time spectrum, then you generate the energy spectrum. So the test setup results, these are some enriched samples I measured. This is a stainless steel foil on the left. This is a 2 micron thick It's enriched. This collected for 6 hours. Now, the new instrument will have, depending on the line width, assuming it's a 3 gamma line width, this collection time would be reduced by a factor of 60. And so this 6 hours would turn into 6 minutes. So this would be the quality of spectrum you would get for this kind of material after 6 minutes with the new instrument, assuming a 3 gamma line width. Percent effect you see is 15%. Percent effect, for those that don't know, this is just the ratio of the absorption dip to the baseline. So 5,000 divided by 35,000, that's where the 15% comes from. The quality refers to the magnitude of the dip relative to the RMS of the baseline, the RMS being the sigma. Typically, you want a quality of about 50 sigma for data or better. Obviously, more is always better, but given synchrotron time constraints, one has to make some compromises generally. So one would probably want to collect this longer. Also, the quality goes as a square of time. So to double the quality would take 4 times the data collection time, just FYI. The sample on the right is a clinopherrocillite. I got this from Jennifer Jackson. Actually, she measured the spectrum here and collected for 24 hours. You see the percent effect and the quality. Again, this is the level that you get for enriched samples. In 24 hours, this would be the level you would get in 24 minutes with a new source, assuming it's a 3 gamma line width. I also measured some natural samples. These are low iron concentration natural samples. They're actually single crystal amphiboles. One on the left is from Mount St. Helens, and these were provided by Bob C. Roshbacher. We collected this for 11 hours. So this is the level you would get in about 11 minutes with the new instrument given a 3 gamma line width. And you see the percent effect and the quality are rather low. These are, like I mentioned, very low concentration. I don't know the weight percent offhand, actually, but I just know there's very little iron in them. And of course, it's natural, so it's 2.2% isotope abundance. But if you convert this to, let's say, the new instrument, assuming a 3 gamma line width, the 11 hours would turn into 11 minutes. So that's the quality you would get after 11 minutes. And you would want to, let's say, if you want a quality of 50 sigma, that's a factor of 5. So you'd have to collect for 25 times longer. 25 times 11, you're looking at about 6 hours. Is that right? No, more like 4.5 hours for this spectrum to get sort of 50 sigma in a very low concentration iron material. And the one on the right is very similar. We counted almost twice as long. This is even less iron. And then you see, so here you'd probably want to collect for almost 8 hours for something with such low iron concentration. So some comments on this approach. The multi-line spectral shape of the emitter is very stable. We're able to characterize it independently, and we know it very well. So, and very stable. I've shown it's stable over hours, but in reality, it's forward scattering from an iron foil, and the iron foil will be capped with gold and in a UHV chamber, or at least a high vacuum chamber, and so it should be quite stable. It's also not sensitive to temperature significantly, temperature, angle, or various things. So it should be very robust. The new instrument should reduce collection times relative to the test setup by a factor of 30 to 60, depending on the line width of the source. And the upgraded instrument will also have like a 1 micron focal spot size. Encona software is available for fitting the spectra. And if people prefer to use other software, of course, I can provide the source spectrum as needed. Just email me. I wanted to mention a new laser heating system. This is in collaboration with Caltech Institute, and this is work that's being done by Sijin Zhao and putting this together. So we have double-sided laser heating. This can be done for both the Mössbauer spectroscopy as well as the vibrational spectroscopy. The first technique, the vibrational spectroscopies, all the isotopes will continue as before the APS upgrade. There will be no real change apart from the focusing capability. For the forward scattering or the Mössbauer spectroscopy, everything will again remain the same except for the iron. In that case, we're introducing an energy domain approach. This instrument should be ready next year, and this produces a polarized multi-line source spectrum with a 1 micron focused beam. There's a potential to do conversion electron Mössbauer spectroscopy, and as I mentioned earlier, if somebody's interested, please send me an email and let me know. We'll have an upgraded laser heating system. Although I didn't discuss it, the beamline has capability for diffraction, owing to the area detector we have. I went fast through a lot of things, of course, and a lot of the information extraction and technique and stuff. So I put some additional papers up here if people are interested, depending on the category or what you're interested, sound velocity or isotope fractionation or Gruneisen parameter general papers. We have data evaluation software. This is software written by Wolfgang Stern, who used to be in our group, and he's retired now, but he continues to maintain this software and continues to update it as well. And it's available for free at this website. We also put on with SEAS a workshop or tutorial annually, typically once a year. Hopefully that continues. This year, it's going to be in a month. I think it's already booked. I'm not sure. But anyhow, if you're interested, let us know. A lot of people contribute to the beamline. The list is actually longer stronger than this. These are the people that are most prominent in terms of various categories, whether it's engineering or beamline support and whatnot. So thank you for your attention.